Hi, I'm Akash Saraf, and I'm the CEO of Zenith Infotech. And what I would like to speak about today is the storage behind Tiger Cloud. The storage architecture of Tiger Cloud is one of the most revolutionary aspects of what we think of a very revolutionary product. Now, when we started building the storage architecture behind Tiger Cloud in 2006, we realized we had to completely rethink the way storage had done. The conventional way SANs are built, the conventional way a NAS is built, had run its course. Luckily for us, we could see 2-3 trends on the horizon which would make our architecture possible. The first and foremost is solid-state drives were appearing on the horizon, and it was just a function of time before they became better and cheaper. What we all know with solid-state drives we can do is get extreme high performance from a small random block I/O standpoint, something the hard drives don't do very well. The second thing on the horizon was, thanks to the industry, they kept building bigger and bigger and bigger SATA drives, higher capacity SATA drives at extremely low costs. Okay? And the third thing was multi-core CPUs. Traditionally, storage processing hasn't been always done by a RAID controller or an ASIC or some kind of a specialized processor which takes years to develop and costs a lot of money. No wonder conventional storage systems cost that kind of money because of the kind of R&D needed to build those specialized pieces of hardware. What we figured out is, as multi-core processors from Intel get cheaper, faster, as they always get, most of the storage processing logic could be done in software rather than having to create specialized hardware to do it. So when we started building out the Tiger Cloud storage architecture, we said there are a number of customer problems we need to solve. And it was interesting. I think we were one of the first in the industry to have one storage product which addresses all these issues. We need a system which is high performance. High performance not only in doing sequential writes and sequential reads, but high performance in doing random reads and random writes, which is the most prevalent form of I/O that occurs in the normal network, be it VDI, be it Exchange, be it SQL Server, be it Oracle. The normal nature of I/O is small block, random, and traditionally hard drives do a very hopeless job of managing that. Well, the second thing was cost. It's great to have this nice storage system and then tell a customer, oh, it's going to cost you $10 a gigabyte for every usable piece of data that you have or usable storage that you have. When we built Tiger Cloud Storage, we said we need to bring that prices down, because if we bring it to that price point, this becomes affordable for every customer out there. 3, we needed a system so which could expand seamlessly. What happens in a traditional world? In the traditional world, you buy storage, you have virtual machines running on that storage. When you start running out of capacity, you go through the very painful process of having to move data from one storage box to another box. We said we didn't want our customers to go through that pain. Okay, to build a storage system, adding storage should be like as easy as adding a box, and the virtual machines using that storage shouldn't even have to know that, look, there was no new storage added. In a way, we're trying to basically virtualize storage. We're making it like how the hypervisor virtualized servers. Our idea was to build a storage hypervisor. We used to call it a storage hypervisor long before the industry caught onto this trend. The next thing we wanted, which is a pretty interesting architecture, is all of us know the pain of doing backups. We needed to build a system where primary and backup storage could be in one single box itself. So no concept of having a primary SAN and then having a software which backs it up to a disk and then disk to tape. Our goal was, as the data was written, it should get backed up. And that's what we tried to do with the system, that primary and backup storage in one box itself, or one system itself. We wanted the system to be extremely reliable, such that if you lost hardware, whether you lost a storage box or lost hard drives, lost SSDs, you shouldn't face downtime. Now, as SATA drives became bigger and bigger and bigger, one of the biggest headaches is when you have disk failures or bit rot problems, you could run into data corruption issues. So the system needed some form of self-healing, where if you have a bit rot problem or disks fail, the system could automatically heal that situation without the virtual machines or your customers getting affected. Lastly, we needed a storage system which is secure. That is, the way we stored our data shouldn't be easily available for hackers to go directly into our storage system and pick out the data. So that's what we tried to do. A lot to do in one storage system. But of course, over 5-6 years of working on this product, we've finally managed to do that. Now, how does this Tiger Cloud storage system work? The basic building block of a Tiger Cloud storage system is what's called a storage node. You can think of the storage node as a highly redundant, supercharged SAN. All right? I like to think of it more than a SAN because I almost feel that the SAN is the architecture of the yesteryears. This is how storage will be done in the future. So you could, as a customer, you could start with one storage node and say that's all I need, or you basically implement what we call is a scale-out architecture. We believe that rather than having one super expensive box, which can be a single point of failure, why not basically take the Google approach, put multiple boxes, which are lower cost, but form a pool of capacity of storage, which is completely virtual. As an administrator, you see only one single pane of glass to administer all these boxes. Virtual machines don't need to know where the physical data lies. And you can add capacity as you need it. So that's what we try to do. So the storage node is the basic building block of our architecture. All these storage nodes connect over a normal gigabit Ethernet network, or if you really like it, we also provide systems with 10 gigabit Ethernet cards. So let's say what a storage node looks like. Well, it's a normal Intel Xeon machine. As I said, we are a big believer in the model that multi-core processors will one day become fast enough where they'll replace the need for hardware-based RAID controllers or ASICs. And that's what exactly happened. Our entire storage system is built out of a standard Intel Xeon CPU, having 2 solid-state drives, 6 hard drives or 8 hard drives, that's configurable. So let's look at the anatomy of what happens when data gets written onto a storage node. So let's say a virtual machine is writing data onto the storage node. In order to provide sub-second response times to the virtual machines, rather than waiting for the data to get committed to disk, we write the data onto memory. And rather than writing data onto the disks in a random fashion, we actually write the data sequentially. We all know the fact that sequential writes on hard drives using larger blocks work 10 to 20 times faster rather than writing small random blocks onto a hard drive. So what we do, virtual machine writes data, goes into memory. We coalesce all these small little writes into one big write. We call it a storage container object, and then dump that storage container object sequentially onto the hard drive. But guess what? It's not only on the hard drives of a single storage node. What our architecture manages to do is, imagine you have 3 storage nodes. So if one virtual machine were to write data to a storage node, using our very, very, very revolutionary erasure coding technology, we actually spread the data across the disks of all the storage nodes in that particular environment. So if you were to lose this storage node, no big deal. Your data is already, we've made enough fragments of this data such that we can retrieve the data from the remaining 2 storage nodes. So what we did with this was made our writing process extremely fast. Whether you wrote a 4K random block, a 64K sequential block, or a 1 megabyte sequential block, the response time and the speed you got is exactly the same. Very, very fast, extremely quick. Now, we all know that when it comes to the biggest performance killer in any storage system is random reads. It's a big headache. So to solve that problem, what we did was we put a couple of SSDs in our storage node, and the way we implemented our caching algorithms, 99% of the I/O occurs in memory and flash. Almost think of it like this way, that the hard drives are actually now becoming a backup system. Most of the I/O which serves up data happens from memory and the solid-state drive. Guess what? What do you get with this? You get close to 20,000 IOPS. I am saying it again. 20,000 IOPS of performance per storage node. So imagine if you have 5 boxes, you would get 100,000 IOPS. Imagine getting this performance 3 years back. You would be buying $1 million system to drive this kind of performance. So again, we came out with a very, very interesting approach where we said, what hard drives are good at is writing large blocks of data sequentially. Let's use it for that. What hard drives are good at is hard drives have immense capacity. So let's store snapshots and retain those snapshots as long as the customers want. Let's use SSDs what they're good for, which is random read for small blocks. So with this architecture we ended up creating was, one is we implemented a very innovative zero-copy snapshot algorithm where we snapshot as data gets written. Rather than having to copy data, we call it zero copy because we don't actually copy data. Each snapshot is only a pointer to a point in time where you want to restore from. We snapshot all volumes on our system every 15 minutes without a problem. And as an administrator, you can decide how long you want to keep that snapshot. 1 week, 15 days, 30 days, 6 months, year, 3 years. You decide, depending on your storage, how long you want to keep that snapshot. Then think of it this way. All these blocks are getting spread across different storage nodes. So it achieves our objective of saying primary and backup should be a single system. I don't need to sit and make backups and keep multiple versions of my old data. I have my restore points right on these boxes themselves. Now guess what? What happens when you may ask me, okay, I'm storing all these snapshots. What happens to me as I start filling up storage? No big deal. We fill up storage, put another storage node. It transparently just creates more storage capacity for the entire pool of storage you have. So you don't take backups. You don't take local backups. Local backups are integrated into the box itself. 2, since we have the snapshots, other than just restoring data, our goal was to allow for unlimited amount of cloning to be done. Let's say you have a SQL database. You want to go back an hour back and say, I need to run an audit. Just create a clone of the SQL volume. Our cloning technology doesn't take an actual physical copy of the entire data. It starts from where you leave. It just is a pointer back to the original or a pointer to the parent. So you can create unlimited clones. And in order to really get the maximum effect from our cache, we implemented what's called a content-based read cache. To keep it simple, what we implemented was deduplication within the cache itself. What does that mean? Though each of our storage nodes comes with between 240 to 480 gigabytes of cache, because we dedupe the data which goes into the cache, the effective capacity of the cache is more like 1.5 terabytes to 2.5 terabytes. What our customers see is 99% of their read I/O requests are coming from the SSD itself, giving them blindingly fast response times and performance. Think of it this way. If you have 40 virtual desktops writing here, okay, all the boot volumes will have only one instance sitting in the cache. I know we ran a test where we booted a Windows 7 machine off our storage node and actually booted in less than 27 seconds. Why? Because again, the data is coming from the cache. So with one product, we managed to achieve all these different objectives. We kept the cost low, as I said. 2, we made it high performance. 3, we made it extremely reliable. 4, we merged primary and backup into one. And 5, we made this easy to expand by just adding storage nodes. As a customer of ours, you do not have to plan upfront how much storage you need. You start with 1 box, go to 3 boxes, go to 10 boxes, go to 15 boxes. It's as and when you need storage, you get storage. Now you're going to ask me, what about offsite disaster recovery? Well, we figured that out and said, okay, we'll build the capability to replicate from one storage node or a pool of storage nodes to another pool. So we have a built-in capability to replicate data between storage nodes or between a pool of storage nodes. So let's say this is your location in New York and you have something similar in San Francisco. On a per virtual machine level, you can say, I would like to replicate my data onto another storage unit. So again, God forbid your New York location goes down. You don't spend hours trying to restore in San Francisco. Because again, for us, primary and backup is single. You just start those virtual machines in San Francisco in less than an hour. So again, what we managed to do with Tiger Cloud Storage is build one system which ended up achieving all these objectives.